Our next speaker is Sultan. He's a researcher, Technology Innovation Institute, Earth observation. Okay, let me start again. Sorry for this. Okay, Sultan is our next speaker. He is researcher at the Technology Innovation Institute, the Department of Earth Observation Situational Awareness Program. Am I right?
Yeah.
Yeah, absolutely. Thank you so much. Sultan, the floor is yours. Please share your screen and give us a wonderful speech.
All right. Can you see my screen?
Yes, we do. We do.
Perfect. Okay, so I will, first of all, thank you for having me in this event. It's really exciting to see all these people from all around the world working, here discussing together all the innovation that they're doing. I will go over a little bit of an introduction of TII and what do I do in TII, and then zoom into Earth observation, and more specifically, data fusion in Earth observation. All right. So TII is a government funded research institute. We are part of an ecosystem. So around 5 years ago, while the while the whole world was busy with COVID, the government of the UAE decided to start this ecosystem under ATRC, the Advanced Technology Research Council. We have 3 companies under ATRC: Aspire, TII, and Venture One. The ecosystem is basically Aspire is a program development and the business, let's say business management. And their mandate is to find the problems around the world and then convert these into research that is applied by TII. And then the next step would be taking this research turning it into a venture and move it on to commercialization. So far we have 4 companies: AI 71, Steer AI, Nabat AI, and Quantum Gate. TII has 10 different research centers covering the critical domains around the world. I am part of the Directed Energy Research Center, and more specifically, my job is to apply machine learning in directed energy problems, basically. So part of this, out of our research center came the Earth observation effort and our Earth observation analysis and capabilities. Yeah. So in our work in Earth observation, we find ourselves needing to do data fusion, fusing different types of data very often. So data fusion itself is not a new topic by any means, but today with LLMs and agentic systems, I think we need to take a fresh look at data fusion and update our perspective. So the motivation behind this is that there's definitely a huge operational demand on this because of the valuable insight that it can bring. But my take on why this is important is that we are trying to build more intelligent systems, right? And we always praise people who have good analytical skills. And I think data fusion will empower or can empower analytical skills for machines. So we always, for us as humans, to find patterns and better understand our world around us and perform better, we are always fusing data in our heads. For example, if you take yourself when you're driving, you're fusing the information that you're seeing, the road ahead of you, with the feeling you're getting from the steering wheel and the sounds you're hearing around you to perform better at driving, right? So I believe that systems, if we are able to bring this analytical thinking to intelligent systems, it will uncover a huge amount of value. So we will not be looking at autonomous driving or like virtual assistants. We will be more specifically looking at Earth observation and geospatial analysis. Now, the typical seminar about data fusion will probably tell you, okay, that there's those three main, let's say, challenges in data fusion. The diversity of the data and the heterogeneity of the data, the alignment of spatial and temporal aspects of the data, the noise and the uncertainty, and all these challenges in data fusion. But I want to try and go further and go through some examples from our work in the Earth observation. And I made sure I included a lot of pictures in my presentation, so I hope it's not going to be boring. So the first point, the heterogeneity of the data, I think for us it is a opportunity and less like more than a challenge. Because imagine if you were able to, okay, you're doing some analysis across a big area, and you're trying to source as many information as you want. You have your sensors, you have as you can. So you have your sensors, your satellite data, and all that. But what about textual information, for example? What if you have an article that describes a spread of damage after an earthquake, or a spread of a disease in a historical era, many years ago, and you want to extract this kind of geospatial information out of this textual information? So I think here is where like LLMs and the differentiators can be basically. The just to cover this and keep it in like some terminology to keep in the back of our heads. The data fusion has multiple layers. There's from decision level fusion, and then feature level fusion, and all the way down to data level fusion. Decision level fusion, think of maybe an if statement that is in a system, for example, an autonomous car that says, okay, if the speed limit is this, if there are those objects around me, I should brake, I should drive this in this speed. So it is collecting decisions from different systems to perform better and make the final decision. And data level fusion, think about multispectral imagery when I'm combining multiple bands from the data that I am collecting to come up with a layer or new features that describe water depth, that describe maybe soil like characteristics or temperature or anything like that. So this is the example about data level fusion. And I think, I mean, from the work that we've done, the deeper or the lower you go in this in those layers, the more domain expertise you need and the more challenges you will start facing. I want to take one example about data fusion. When we worked with AIS, somebody here mentioned this ship information system. And let's say you have this huge amount of data and you want to make sure to standardize it. So you want to include it and fuse it with other types of data. The first step you would do is you want to clean this data, right? First of all, AIS is the automatic identification system. It is used by ships to declare their location, their flag, their type, their speed, and some other information about the ship. And this signal is picked up by ground stations to monitor ship behavior and location and so on. So, and this on the right is a ship density map, which is an amazing way of showing ships activity over a period of time. But to come up with this, to be able to fuse it with, for example, weather data or and so on, there are challenges. And so I'll take you through some of the steps that comes after the data cleaning, right? So first is the data cleaning. Like if you're working with AIS data, you will see so many weird behavior. You will see some ships that only sail apparently to the right and left. you will see this ship that is sailing in the mountains. You will see this ship that is on the side, parked on the side of the road. It's a oil tanker. Of course, all of this is anomalous data. And this is an interesting example where you'd see ships having this circular behavior where obviously this is on land, so it is anomalous data. But also this can be confused with other behavior where when the ship is anchored, with the tidal like movement, it tends to do this circular behavior. So it's difficult to tell the fake ones from the correct ones. Now, let's say, okay, your data is clean now. What is next? Usually when we're talking about fusing GIS data, you end up needing to have to grid your area into like 100-kilometer grids or like 10-kilometer grids, and filling your information in those cells. You need, and then you will need to find a summary statistic to fill those cells, right? And we can say that it is density, but what exactly is density? The European Marine Observation tried to answer this question. They started with calculating the number of ships that are in each cell in a certain time. So the first one here on the let me see, pointer. The first one here is their early model, where they just count the ships in every cell and give it a number. Here, it doesn't really tell the difference between those two ships, those two cells, because this one seems a little less dense than this one, but they are given the same number. So they moved on to calculating the distance that is traveled by the total, like all of the ships in that cell in that area, in that period of time. And they ended up with this one, but it also kind of says that this one and this one are the same value, but this one had one ship and this one had two ships. So it was not quite there yet. So they moved on to counting the number of messages that are sent in every cell, that are intersecting with every cell. But also here, this doesn't take the concept of time that each ship spent in that cell. So it's still not there yet. So this is 6 and this 17, but the difference is actually bigger than that, I think. So they ended up doing it in this way, where they count actually, they normalize kind of the distance between every 2 points, and they depend on the time, the total time ships spend in that cell in that period. So, and they right now the image you saw was basically calculated in this way. Yeah. If you do that correctly, you will end up with this amazing type of visualization that can be fused with other sources of data. Another example is ADS-B. ADS-B is similar to AIS, but it is for airplanes. Sorry, I'm going over the time here. I'll try to wrap up. ADS-B is similar to the ship, to the AIS, but it's for airplanes. We thought, okay, we did this for AIS, let's do it for airplanes. But it turned out there's a unique set of challenges there as well, because we found that airplanes would shut off their transmitters even before they reach the docking position in the airport. So we tried to do this to label or to validate our detection model that detects airplanes in SAR data. So we ended up having to write like an algorithm to collapse all the ADS-B data and make sure that, okay, when we have a SAR image from this time, we have the correct or the most correct ADS-B data from the ADS-B database. All right, so that's it about it. I want to introduce some of the challenges that TII does. So there is the series of challenges that TII does. It's called the crowd challenges. We've been doing we did 4 or 5 so far, and it's been a great success. We launched these international challenges, and we will be announcing Earth of the observation challenge, which will be around the topic of data fusion. So if you're interested, it will be a great opportunity for you to show us what you can do. The previous challenges had prices of around like $50,000, $55,000, somewhere around that area. This is if you can use this QR code to check out the website. The priority sectors of the challenge and our work in general, our Earth observation work in general, are 6 priority sectors. First is agriculture and environment. This image is multispectral data that we used to predict coral reef health. And the second priority sector is maritime and coastal. This is a multispectral image that we use to find the to perform bathymetry and find water depth in a port. Urban and infrastructure. This is interferometric SAR. It is a really cool analysis. We use SAR to monitor land deformation and subsidence, and it's very, very accurate, like down to the centimeter or even to the millimeter. Public health and safety. This is a multispectral image that we used to detect harmful algae blooms. Energy and utilities. This is mineral detection using multispectral data as well. This is hematite. And this is just a bonus image, magnetic data. I like this image. And we also have the equipment to run our own magnetic data surveys. So yeah, that's all for my presentation. This is the QR code to our Earth observation website. You can visit it and you can see all the details, more details about the things I covered in this presentation. And stay tuned for the Earth observation challenge.
Thank you so much. Thank you so much, Sultan.